Boundary condition for electric field. Why boundary condition is important? So when wave is going to propagate, it will have different interface. So that interface, how it's going to change the electric field components as well as flux density in case of electrostatics. So here, first you'll understand what is the meaning of this boundary conditions. So when interface is going to start, at that interface, we have boundary. So to understand this various situation, first we have dielectric and dielectric. So where one medium having different permittivity, another medium having different permittivity. Next, we have another situation of between conductor and dielectric interface. Then we have between conductor and free space. To understand this interface condition, we should recall the concept of Maxwell equations. We have seen how many Maxwell equations? In electrostatics, you have two Maxwell equations. Okay. So here, this Maxwell equation is in the integral form. E dot dl over the closed path is equal to 0 and total flux is equal to charge enclosed. So this D is the flux density in case of electrostatics. So finally, total flux, okay, that is d dot ds surface integral over the closed surface, that is equal to the total charge enclosed. So this concept we are going to utilize here to understand this boundary condition or interface. So here if you see that we are going to take the tangential as well as normal components of this electric field as well as flux density. So this E suffix T is going to represent the tangential component, E suffix N is going to represent the normal components. So first of all, we are considering the condition between dielectric and dielectric. So here, this is the boundary between dielectric, which having permittivity is the epsilon 1. Another medium is also dielectric with permittivity of epsilon 2. So already you know that this epsilon is equal to epsilon naught into epsilon r. Okay. So epsilon naught is the permittivity of free space. Epsilon r is the relative permittivity. So already we have lecture based upon the dielectric constant and all, you can read there. Now here in case of medium 1, we have taken this electric field intensity is the E1, and for that we have tangential component E12 and normal component is E1n. So generally if you see that, suppose for example, here our electric field component is like this. So when we'll resolve two components, so that tangential component you'll get E1t and that normal component you are going to get here, that is E1n. Now to obtain this in a triangular shape, to get the resultant vector, this E1n is shifted here. So that's why situation you are getting like this. Similarly, in case of medium 2, again we have this is the electric field intensity in the medium 2. For that normal component, that is the E2n, and tangential component is E2t. Again we have shifted this tangential component here to form the resultant vector. Now here on this interface, we are going to consider the differential path. So that path you are seeing here, we have A, B, C, D. So here direction of the arrow is important. So here we are going to move in the clockwise direction. On the basis of that, later you see that we are going to write the expression here, okay, for the electric field intensity and we'll see that how we'll able to obtain the flux density. So right side, if you see that here at the interface, we are considering the differential surface, that is the del S. And again here we have normal components as well as tangential component of the flux density in the medium 1. Similarly, in case of medium 2. So now this differential surface that is the consider here, it is the cylindrical shape here. So for that, base area is the del S and height is the del H. So finally, on the basis of this consideration of this differential path, we are going to see that equation, and later you'll find that here tangential component of electric field will be equal and normal component of flux density is going to be equal. So that derivation we are going to see. Now it is important that in the medium 1 and medium 2 when we are going to move. So that medium we have considered that at the interface, okay, we have situation like this. Okay, this one direction we are considering in the clockwise. So that path is A, B, C, D, A. Okay, so here in the medium 1, this is the del H by 2. Okay, from here to here, and from here to here we have again del H by 2, and this width we have taken del W. Okay, so finally in this considering the path ABCDA, so finally what we have here by using the Kirchhoff voltage law, you know about this. Okay, so total potential, sum of total potential is going to be equal to 0. So finally for this A to B, what is here? Tangential components. If you see that this is the E1T, so that tangential component in this situation we have same direction in which we are moving. So this is here E1T, this is our E1 and this is E1N. Okay. So finally now if you see that for the A to B, we have E1T and width is the del W. Now here for B to this part, upper part of here, from here to here, okay, this we are moving against the normal component. So sign is negative here and height is del S by 2. Again from here to here to reach the C. Now we are moving against the normal component of this electric field intensity in the medium 2. So this is the E to T and normal is in this way, that is E1N. So finally we are moving against, so that here we have again negative sign. Okay, so that is E, this is the for the medium 1 upper part, that is the for the this portion, minus E2N del S by 2. Now we are going C to D. So now again we are going against the tangential component. So that sign is negative, E to T into del W. Now here we are moving to the medium 2 for this portion. So we are going in the same direction of the normal. So this direction is taken as the positive here, sign E2N del H by 2. Again in this portion from here to here, again we are in the same as the normal direction. So it is positive. So plus E1N del H by 2. So now finally what we are seeing that this component and this are being cancelled out. Again this and this both are being cancelled. So finally we are left with 0 equal to E1T into del W minus E22 2T del W. So finally after rearrangement here we have E1T equal to E2T. Here we are considering that del S tends to 0. So almost at interface that height is going to be 0. So finally what we are seeing that electric field intensity tangential component is same at the interface. So that is the its about the boundary condition for the dielectric in case of electric field intensity. So this tangential component is same. It shows that its tangential component is continuous. Okay. And there is no charge region. We are considering del S tends to 0, very small. Now, if we talk about this flux density here in this dielectric itself, so for that again we have to take the components. On the basis of that we are going to analyze. So now flux density, you know already it is epsilon into E, okay, and it also having tangential component and normal components. And here we got at the interface E1t equal to E2t. So finally E1t can be written as D1t divided by epsilon 1, E2t equal to D2t by epsilon 2. Okay, so finally this 2 is going to be equal in case of flux density. So this tangential component goes through some change here. It is not equilibrium, right? It is discontinuous. So finally, differential charge at the interface del Q equal to rho S into del S, where rho S is the surface charge density. So finally, it is the normal components upwards in the medium 1. So that is D1 and del S. In the medium 2, it is coming downwards. So it is minus D2 and del S. So now at the boundary, so D1n minus D2n equal to del S. Now if it has no free charge, okay, so it is going to become the free charge regions, means charge is not available. So then charge density will become 0. So once rho s is equal to 0, then normal component of flux density is equal. So normal component is equal, that means flux density's normal component is continuous across the interface. So finally, on the basis of this, again, you can realize the expression of this electric field intensity here. So finally, already we know D equal to epsilon into E. So on the basis of that, again, we can write the expression for electric field intensity here. Now, if refraction, so this is another situation which is very, very important. Okay. So this is going to be much useful in case of when wave is going to propagate. So now in case of refraction means wave is going to travel from one medium to another medium. Okay. So later we will have transmission coefficient, reflection coefficient, all these things are there. It is about the refraction. Okay. So now here we are considering that this E1, okay, is making angle theta 1 with the normal in the medium 1, and E2 is making the angle theta 2 with the normal in medium 2. So this is the normal at the interface. So again, for this we have tangential component, normal component. For the medium 2 also here again for E2T, E2N. And again for the flux density also, we can see here we have tangential component and normal component in both medium. So now on the basis of sine and cos values, so if you see that component, so in general, suppose for example, we have some vector. This is the E1 here. If it's making an angle theta here, so what will be its vertical components? So that vertical component is going to become E1 cos theta. Okay. It is medium 1, so theta 1. So this is only what? E1n. And whereas this is going to become E1 sine theta 1. So this is what? Tangential component of E1t. So that's why we have written here E1 sine theta 1 equal to E1t, and here E2t, and finally what we have here E2 sine theta 2. So this is for the medium 2 and this is in case of medium 1. And already we have seen that tangential components at the interface is equal. So on the basis of that we can write E1 sine theta 1 equal to E2 sine theta 2. Okay. So here again similar situation we want to realize in the medium 2 also. Here what we have E2, this is the angle is what? Theta 2. So normal component is E2, here E2 cos theta 2 and this tangential component is going to become the value E2 sine theta 2. Okay, so like this we are going to resolve this vector E1 and E2. So finally, in case of, so already why we have considered the tangential component means already we have seen that tangential component of the electric field intensity is conservative at the boundary. And similarly, normal component of the flux density is the conservative at the boundary. On the basis of that, we are writing here. So finally, already you know D equal to epsilon into E. So on the basis of that, we are going to write here normal components. So this is the E1 cos theta 1. So that's why epsilon 1, E1 cos theta 1, and here epsilon 2, E2 cos theta 2. So normal components are equal. So finally, this left and right both are going to be equal. So now we are going to divide equation 7 with equation 8. Then you see that. So we have expression for sine theta by cos theta. So sine theta by cos theta is going to become tan theta. So on the basis of that, here we have tan theta 1 by epsilon 1 and here tan theta 2 by epsilon 2. So epsilon is equal to epsilon naught into epsilon r. On the basis of that, epsilon 1 equal to epsilon naught into epsilon r1. So epsilon naught is the permittivity of the free space. Epsilon r is the permittivity of the relative permittivity of this dielectric medium. So that is epsilon r1 here and here epsilon r2. So finally we can write tan theta 1 by tan theta 2 equal to epsilon r1 by epsilon r2. This is called as law of reflection. Like in case of light, you are talking about the Snell's law and all these things. Here we have law of reflection in case of electric field and at the boundary, which we consider charge-free regions. So charge density is what here? 0 at the boundary. So this is the one of the situation where we have seen how interface is going to play the role. Okay. So so at the interface between two dielectric produce the bending of the flux line as a resultant of unequal polarization changes. Now here we have second situation where we are considering conductor and dielectric interface. Okay, one medium is conductor and there is the dielectric. So here we are going to consider the perfect conductor. So perfect conductor means electric field is going to be 0 and conductivity is infinity, and so that's why here that charge density is going to become 0. So finally this here, this is the medium 2, this is the medium 1. Medium 1 is taken as the dielectric, medium 2 as the conductor. Okay, here also medium 1, medium 2. So in the medium 2 is conductor, so there's no electric field, no flux density. So everything we are going to discuss in terms of medium 1. So again, we are considering the here closed path, and here we are going to move in the anti-clockwise. As per that, we are going to take the direction. It is important, however you are going to move, that's not important. Important is how you are going to consider the direction of the electric field. Okay. So here only one electric field is there. So that's why we are not writing E1 or E2. Only we have E. It has tangential component as well as normal component. Similarly, for the flux density also, we have tangential and normal component. and we are writing D alone. Okay. And epsilon is epsilon naught into epsilon r, that we know very well. And again here differential area we are going to consider the interface, that height is the del h. Okay. So same as the previous situation, now here we use the KVL. Okay. So now here if you see that in this path, in the medium, when we're talking about the closed path A, B, C, D, A, so when we'll move from A to B, so electric field is not available, so 0 into del W. Again for this portion, electric field is not available, so 0 into del H by 2. Now for the upper side, the electric field normal component is available for this path. Okay, so that is the En into del H by 2. Similarly, again we'll move from C to D. So again here what we have, we are moving against the tangential component. So it is minus Et and width is del W. Now we'll move to this portion. So there again we are moving against the normal component. So minus En del H by 2. And for this path again electric field is not available. So 0 into del H by 2. So finally, what we are seeing that in this situation, this component is cancelled. So finally, what we are getting here, tangential component is going to become equal to 0. Whereas in case of dielectric, what we have seen, tangential components are equal. ET1 equal to ET2. Here in case of conductor to dielectric, tangential component is equal to 0. So these are the important concept that we are looking here. Now again, in this, we will try to see the expression for the normal. So finally, for the flux density, if you're going to consider in this part, so what is the value? Again, okay. So already we know from this flux densities concept, and by using the that we have total charge enclosed, okay, is equal to the that is, you can see this is the by using the Gauss laws. Okay, so del Q equal to dn del S minus. So here this is the medium one, this is the medium two. So medium two, electric field is not there, so flux density is also 0. So finally here dn equal to del Q by del S. So del Q by del S is what? It is the surface charge density. So finally, normal component at the interface in case of dielectric and conductor is equal to rho s. And similarly, here you can see that here in this case, when tangential component, so D is what? Epsilon into E. So finally, here what will have? dt by epsilon. Okay, dt by epsilon will be equal to 0. Similarly, for the electric field here we can see dn is what? Epsilon into En. That is going to become here rho s. So finally, En equal to rho s by epsilon. Okay, and epsilon is epsilon naught into epsilon r. Next we have third one is the conductor and free space boundary conditions. So in case of this, it is the simple, not like first one. So here what we have, one medium is conductor. So this is the medium one, that is the free space, and medium two is the conductor as before. But in place of dielectric, now we have taken medium one as the free space. So in case of free space, this relative permittivity is going to be equal to 1. So that's why now here if you see that situation will be same how we have in case of dielectric and conductor interface. What is going to change here? Epsilon r is going to become equal to 1. So earlier in case of conductor and dielectric, what we got? Et equal to 0. Okay. And there we have dt equal to epsilon into what? Epsilon into Et. Here what will get? Epsilon naught into Et. Since here relative permittivity is equal to 1 and epsilon is what? Epsilon naught into epsilon r. Okay. So this value is Et is 0. So that's why tangential component of flux density is also equal to 0. And we have seen that normal components of the flux density dn equal to rho s. So finally, d is what? Flux density is epsilon into En. So this epsilon will become here epsilon naught only, since epsilon r is equal to 1. So finally from here, En equal to electric field intensity normal component is rho s by epsilon naught. So E field must be approached a conducting surface normally. So this is the situation what we have seen here. So it is very important question for the examination point view, whether it is the GATE exam or it is the university exam. Okay. So watch it again and again, like, subscribe, share with your friends. Thank you. Thank you very much. Thank you.